Hear me? Yes. Okay, so in these last two lectures, I will do the last topic, which is record statistics. So again, we have our basic picture. So think of this time series. Etc. Okay. So this is xi versus I. Okay. And so record means, so we say that I look at a time series of n entries. And most general case, they are drawn from some joint distribution. So we say that the record happens at step k if the value of that entry, kth entry, is bigger than all previous entries. That means it's bigger than the max of x1, x2, x3, x2 minus 1. Okay. So that's the definition. So by this definition in this particular figure, so first guy is always a record by definition because there is nothing before that. So this is a record. This is a record because its value is bigger than the previous guy. This is not a record. This is a record. These are not records. This is a record. And these are not records. Okay. So typically if I go up to, let's say, n entries, then there will be some number of records. So we'll denote by m. So this is a random variable. So in this particular example, we have 4 records. So it will fluctuate from sample to sample. And we want to know what is the statistics of this guy, given this joint distribution. So that's the problem. So in particular, we want to know, for example, what is the distribution. This is the PDF of m given n. So this is the first object. Then you can also ask, if you say, I mentioned that these are the ages of the record. So for example, this guy, didn't survive one step, it got broken immediately. This guy survived, one, his age is defined as the distance between time distance between two records. So this will be L2, this will be L3, and till the end, in general, it will be Ln is the last. So if you have m records, then I have a set so this is the ages of records. And you can ask the statistics of ages of records and so on. Okay. Right. So as usual, it depends on what this structure of this joint distribution is. So we'll again discuss 2 models, basic models. So this is the IID model. where the joint distribution, by now you all know this by heart. This is just the product of the individual distributions. And the second model, as I said, this is a model where there is no correlation between the entries. And the model 2 will be the random walk model. The two favorite models that we discussed, where the entries are very strongly correlated. So let's start with model 1. So how do I calculate the statistics of M? So one natural way to study this problem is introduce a binary 0-1 variable at every step k. You'll see in a minute why I'm doing this. So I define a binary variable sigma k at the kth site, kth entry, which takes value either 1 or 0. So 1 if a record occurs at step k, and 0 otherwise. So for each configuration of your entries, I can find out what is the value of sigma 1. So sigma 1 is 1 because this is the first entry is a record. Sigma 2 is 1. Sigma 3 is 0. Sigma 4 is 1. Sigma 5, 0, 0, 0, 1, 0, 0, 0, 0. So any configuration of the entries, I can associate a string of sigmas, which tells me where are the records. Okay. So then the number of records, because it's 1, 0 variable, clearly is sigma k equal to 1 to n, right? Because this will count, this is like an indicator function, so this will be 1 if there is a record and 0 otherwise. So therefore, it just counts the total number of records up to step n. And this is a random variable. Because the sigmas will fluctuate from one configuration to another configuration. As a result, M will also fluctuate. And we want to know what is the mean of M, what is the variance of M, what's the distribution of M. Okay, so that's the problem. Okay, so let's start with the simplest thing, mean number of records. So I have to take an average of this, average with respect to this joint distribution. So this means from here, if I take the average, okay, where this sigma k average is usually called record rate. This is just the probability that a record occurs at step k. Right? Because sigma k has value 1 or 0. So if I take the average, so this will be 1 into probability that there is a record, plus 0 times probability is not a record. So this is just the probability of the record. Probability that a record occurs at step k. And sometimes in the literature, this is called the record rate. It is the rate at which record occurs. So what we'll see in a minute that, this is quite easy to evaluate this quantity sigma k. So let's do that. I mean, let me first do the computation and then you will see that you could have guessed this result without doing the calculation. So sigma k, so I'm asking that the kth entry, what is the probability that this is a record? So suppose that it has a value r, okay, that kth entry. So if it has a value r, or x if you like, so let me write it down first. So I look at suppose this is the kth entry. Suppose its value is x, okay? So if its value is x, by definition, all the other guys have to be less than x, right? So therefore, and since they are IID variable, and there are k minus 1 of them previously, before this guy. So it's just this, and I have to integrate over from the value of x itself. They are asking what's the probability the record occurs. It can occur with any value, and so I have to sum over all possible values. And so this is the answer. Okay? Now on the face of it, it looks like it depends on p of x. But again, if you define, just make a change of variable. So this means the du dx dx. So if I just do this change of variable, dx dx is du, and I have e to the power k minus 1, and the limits are from 0 to 1. And this is just 1 over k. So already you see that is first of all universal. No matter what the distribution p of x is, this record rate is universal, it's 1 over k, it does not depend on p of x. Okay? And in fact, the mechanism of universality is precisely this change of variable, because any distribution, cumulative distribution, you can map it to a uniform random variable between 0 and 1. U has a distribution which is uniform between 0 to 1. So therefore, this is just any distribution by this mapping, you can map it to the universal, to the flat distribution. And that's the sort of mechanism that why this becomes independent of p of x. Now this result, if I now tell you, you think a little bit. I mean, you don't care what happened after that. Your entry can be as big as you want. So you're looking at this particular, sub part of your sequence, and you're asking, what is the probability that the record occurs here? Now, if a record occurs here, this is the last of these steps. So that means, record means that means this guy must be the global maximum, because it has to be bigger than all the other previous guys, right? So the probability that the record occurs here is probability exactly that the T max, what we did in the last class, T max is exactly equal to k. Now T max is uniformly distributed, we have seen that. So therefore the probability that T max will be k is just 1 over k, right? We have seen that it's a uniform distribution. So this is just, so basically any of the k guys can be the last guy, can be the maximum. So what's the probability that the last guy is the maximum? Is just 1 over k. Okay? So this kind of arguments, of course, is nice to cook, but I mean, you should always back it up with some algebraic calculation where you see exactly how it's coming. Okay? After that, you can use these kind of arguments, but it's always a bit dangerous to use, probabilistic arguments without doing a proper calculation. Okay, so this is just to illustrate that. Okay, so what this result means is that as k increases, that means, you are asking what is the probability that the record occurs at step k. As k increases, so this decreases with increasing k. Very slow decrease as 1 over k. But this means that, it gets increasingly harder to break records. The more you go in your IID sequence, to form a record which is intuitively clear, I mean, if a record happens for the next guy to be a record, it has to exceed already this value. So it becomes harder and harder to create a record. And this record rate there, it actually goes like 1 over k. Okay? So then the expectation value of m, therefore, if I just put this exact result, so it's just 1 plus half plus 1/3 plus 1 over n. So this is the harmonic number. It's called harmonic number. And this result is very beautiful because it's totally universal, does not depend on px, and it's an exact answer for any n. And in particular, for large n, because you're always interested in what happens large n limit. So large n, as you know, this sum over 1 over k, it goes like log n. You can even calculate the correction term, which is order 1, and then there will be a higher order corrections, order 1 over n. And this constant is called the Euler constant. I mean, you should try to see actually that how this number goes to log n and how do you actually calculate this Euler constant. Its numerical value is about 0.57721. So this says that the number of records actually increases very slowly with n. So you go up to very, very long sequence. Number of records, of course, you expect it to increase, but increases very, very slowly as log n. And that is because it gets increasingly harder and harder to break the record. And it increases very, so if you plot Mn, average Mn versus n, it increases like log n, very, very slowly. If the record was broken at every step, that would have gone linearly with n, but this actually increases very, very slowly as log n. Okay? So this is the mean. So now let's calculate the second moment, for instance. If you want to compute the variance, fluctuations around the mean. So again, my definition of m is this. So m squared will be expectation value of that. Now in this sum, so there will be some diagonal terms when k1 equal to k2. So let me call this object as ck1, k2. So the diagonal terms are basically c kk when k1 equal to k2. Because when k1 equal to k2, then this is just sigma k square. But sigma k is a binary variable, 1 or 0. So sigma k square is exactly 1 or 0. So sigma k square is exactly sigma k. So diagonal element is very simple. It's just 1 over k again. But an off-diagonal element, so clearly, ck1, k2 will be same as ck2, k1 because it's just sigma k1 times sigma k2. So we can just consider k2 bigger than k1 because k1 less than k2 will be exactly identical. It's a symmetric matrix. So when k2 is bigger than k1, then we want to calculate this object. How do I calculate that? Exactly same way. So suppose this is k1, and what is this is the probability that the record occurs at step k1 and another record occurs at step k2. So I look at k1 and I look at some other later point k2. I want both to be records. I don't care what happened in between, but these two endpoints, the k1 and k2, should be a record because this will be 1 if both sigmas are 1 and 0. If any one of them is 0, it's 0. So this is therefore the probability that both k1, k2, both are records. Okay? So to compute that, we'll follow exactly same procedure. So let's say the value of this guy is x as before, and the value of this guy is y. Okay, so what are the conditions? So let me write it down first, and then we'll explain. Okay, so suppose that this guy's value is y. So what I need, therefore, is that these objects, how many are there? K2 minus K1 minus 1. So many elements are there in between. Okay. So those guys, their value, their value have to be less than y certainly, because if y is a record, it has to be bigger than all the previous values, including these guys who are in between these two records. Okay. So suppose I fix this guy x, so I have to ensure that all these guys here, they are less than y, such that this is a record. So therefore, py prime, dy prime, all the intermediate guys, they should be less than y. Okay, so I'm giving you y and x, and then these guys have to be less than y. There are K2 minus K1 minus 1 of them, intermediate between the two things. And then this is the K1 guy, which has value x. And then I have to ensure all the guys previous to x, K1th guy, they should be less than x, right? So this guy is x, and this is a record. Therefore, all these guys should be less than x. And the probability for that is minus infinity to x, px prime dx prime to the power K1 minus 1, because there are K1 minus 1 guys before that. So this is the probability of this string. And then I have to integrate this x value. The x value can be anything. Only thing is that it should not be bigger than y, because y is a record. So everybody here, and this guy itself, they have to be less than y. So therefore, x integral can go only from minus infinity to y. And finally, we want to evaluate all possible value of the record at K2, which should go from minus infinity to plus infinity. Is that clear? Okay. So, and then you use the same trick. So you make a change of variable. So let me call it U1. So I have a double integral, so I have to define two variables. So then you see immediately, if you just make this change of variable, that this is just y is associated with U2. It's the same trick basically. So you map it to any cumulative distribution to uniform distribution. Okay. Just, this is exactly same trick. And so this guy, when you do, so this integral gives me u2 to the power k1 divided by k1, and this u2, this power cancels with that. So you are left with u2 to the power k2 minus 1. When you do that integral, you get just 1 over k1 and so 1 over k2. But 1 over k1, 1 over k2, when k1 is not equal to k2, so this is just expectation value of that. So what we see is that for any k2 not equal to k1, any off-diagonal term, sigma k1, sigma k2 is exactly sigma k1 times sigma k2. So this means that the sigma variables are actually uncorrelated with each other. So whether a record happens here at step k1 and another record happening k2, they are actually essentially independent events effectively. It's not obvious statement. You see that in retrospect. And This is quite a remarkable fact, okay? And then, which I'll not do in the class, so you can do the same exercise, so I'll leave it as an exercise. So now instead of K1, K2, you go up to generally this kind of correlation function. You take n such records and you ask what's the expectation value of that. And again, when these indices, when they are not in the same place, this you can show that this is exactly uncorrelated. Okay? So essentially these sigma variables for this IID problem, so these variables, they are essentially, these indicator functions, they are completely, independent, uncorrelated. Not just for 2-point function, any n-point function. Sorry?
If the sigmas are uncorrelated,
Yes.
that doesn't imply that sigmas are independent.
Of course it does.
No, the opposite is true. I don't think the uncorrelatedness implies.
Why do you think I'm doing the n-point correlation function? You got it? If you can prove it for any n, then they are uncorrelated. Okay, so essentially, therefore, because it's valid for any n, therefore they are totally uncorrelated, these sigma guys, basically. Okay, and so let's calculate then the variance first. Okay, let's second moment. So we said second moment was sigma k1, sigma k2, expectation value. K1, K2. I have to separate out the diagonal elements. So that's sigma k when K1 equal to K2 plus when K1 is not equal to K2. So this, we know the answer, 1 over K. And this guy, we know that this is sigma K1, sigma K2, which means basically 1 over K1 times 1 over K2. Okay? And this guy here, 1 over K1, K2, you can actually simplify it further by saying this is 1 over K for diagonal terms plus K1, K2 without the equal to sign. So I just add and subtract the diagonal term again in the product. So you have that. But this guy is just the, average m square, right? Because there are two sum here and including all terms. So this is just average m square, okay? So therefore what you have is, if I now calculate the variance of m, you cannot see probably here. So therefore variance of m, which is m square minus n square. This is, so there's an exact formula, which is because you take out the average m square on the left hand side, so you are left with that. Okay? So you can evaluate it for infinite k. In particular, again, for large n, this first term here, it goes to log n plus Euler constant, as in the case of mean. And the second term, you know that 1 over k square, when you take from k equal to 1 to infinity, this is a convergent number, is pi square over 6. So therefore, this constant is pi square over 6 plus order 1 over n. So therefore, mean was exactly going like log n plus gamma e, and the variance also goes like log n for large n. Okay? Okay, so mean and variance, and now I want to calculate the full distribution. So how do I calculate that? So we have seen that M is summation sigma k. So let's consider this object. So this object simply means it's just a generating function of the distribution of maximum. So now this means lambda to the power summation sigma k. But the sigmas are uncorrelated, so therefore this is just and sigma 1, so this is, what is this value? So when sigma is 1, it takes value lambda. And what is the probability that its value is 1? Is 1 over k, we have seen that. And when sigma is 0, it takes value 1. So that happens with probability 1 minus 1 over k. Because this is the 1 over k is the probability that sigma is 1. 1 minus 1 over k is the probability that sigma is 0. Therefore, this object is just this guy here. Okay? So this is just 1 plus lambda minus 1 over k. So this is sigma k. Right. So therefore, I have a product of all of them. So therefore, the answer is k equal to 1 to n lambda minus 1 over k plus 1, which is, the point about generating function is that if you know the generating function, this is the exact generating function. Okay? And if I know this generating function, then I can just expand it in lambda and find out the coefficient of lambda to the power n, m, and that is exactly P of n. Okay? So what is this coefficient? If I expand as a power series in lambda, so then this is okay. Well, these objects, this is not binomial. So these are actually, there's a name for it. It's called the unsigned Stirling numbers. They are combinatorial objects which appear in problems, for example, in random permutation. So if you take an integer and you take all possible permutations of it, there are n factorial of them. And if you calculate that how many disjoint cycles are there, so that is how many disjoint cycles are there in a permutation of sequence n, I mean 1, 2, 3 up to n. So this is just the number of, so the number of something called disjoint cycles. But anyway, this is some combinatorial object. These are well-studied objects. So if you put these values there, so therefore what you have finally, the comparing both left and right hand side, this guy and that guy. So what you see is that the probability that I have m records, that's exactly 1 over n factorial into this Stirling number. So these are well-defined objects. I mean, they are, you can compute them explicitly. So for instance, if I take n equal to 4, so if I take an entry of 4 entries, then number of records can be 0, or 1, 2, 3, or 4. So I just evaluate these numbers, you can find out. So this is 0. So this is 0 by definition because first guy is always a record. So the probability of having 0 record is exactly 0. What's the probability of having 1 record? So I have to put here 1 over 24. And the Stirling number there is 6. You can read it off from the well-known, from Wikipedia page or whatever if you want. So this is 1 quarter. Probability of 2 will be 11 over 24. Probability of 3 will be 1 quarter. And this is 1 over 24. So it's very nice combinatorial structure. So these are well-defined, well-known objects. So you have an exact full distribution of the number of records, which you can read it off from there. So you can just ask Mathematica to plot them, and what you will see is that the plot of P of Mn versus M, it typically has a peak, and the peak will occur around the mean value, okay, which we have seen is harmonic number 1 plus half plus 1/3, etc. 1 over n. And then there's a variance around that. So for large n, this mean goes like log n. The variance also goes like log n. So the width, which is the sigma, standard deviation, will go like square root of log n, whereas the mean will go like log n. And in fact, you can use to calculate the asymptotic behavior for large n and large m. You can use, again, the asymptotic well-known properties of Stirling numbers. I'll not do it here. You can actually deduce it also from the generating function directly. I'll just tell you the results. This is what you would guess. Actually, you could have guessed this result directly from here because I just proved that sigma k's are uncorrelated variables. And so I have a sum of n independent variables. And therefore, by central limit theorem, you will guess that, again, M would be a Gaussian distribution. And so for large n. So it's centered around its mean, which is log n, and its variance is also log n. So this is the Gaussian distribution. Again, just follows from central limit theorem. If you know the mean and variance, you are done. But this is an exact formula you can evaluate for any finite n. And you can also calculate, for example, the large deviation tails far away from the mean from this general formula. But basically, this is the distribution. So again, this distribution, you can write in the scaling form. Remember, we are always writing in the scaling form because that's our favorite way of writing. So if you like, this is the AN and this is the BN, like in the extreme value statistics. This is centering and this is scale factor. And this scale factor 1 over square root of log n must be there in order that it's normalized to 1. And the scaling function, this G stands for Gaussian. which is normalized to 1. So that means for large n, essentially, this will converge into a Gaussian distribution with this mean and with this standard deviation. And so that's the sort of, so for IID variables, so main thing is that, again, the full distribution of the record is totally independent, it's universal, it's independent of the underlying distribution P of x. If you take Gaussian, if you take uniform, you can take Levy flights, whatever you want to take. But the final result for the record statistics is totally universal and is essentially centered and scaled record number is distributed via Gaussian distribution. Okay? So this is the sort of main result. Okay? And then you can also ask, what about the statistics of this L1, L2, L3, LM, etc., record ages? You can calculate all these things. I will not spend time on that. But for instance, just to show you some results. So if you calculate, for example, the Lmax. Lmax means out of all these records, you're asking, so which is the guy which actually, for which the record survived the longest? So it's the longest larving service. So you are looking at the maximum of all these record ages, and the guy which is survived the longest, so like Tendulkar's, I don't know, 51 centuries, which I suppose will stay for a very long time till somebody like Joe Root or Virat Kohli takes over. So Lmax, you can ask, so longest lasting record, how does it scale? So as n goes to infinity, large n limit. So this actually scales linearly. Okay. So you have a sequence n, of sequence number n, and this is a constant, which is called the Coulomb-Dickman constant. So it has an expression quite a non-trivial expression, and its numerical value is about 0.6243, etc. So this means that the age of the longest lasting record is almost proportional to the full system size n with a prefactor which is 0.62. Okay. So that means, that guy, longest record lasting, basically 62% of the people, total number of people, will be less than that value essentially, and on the forward direction. So this is the fraction of guys which will be, this guy has survived for so much of it. So this length is almost proportional to the full system size, the biggest guy. Okay? But the shortest guy, on the other hand, you can ask shortest lasting record, how does that guy scale as n goes to infinity? So that indeed scales like log n with a prefactor which is e to the power minus gamma e, where gamma is again is the Euler constant. So you can now work out, many of the other very interesting properties, and you see that all these things, they're quite non-trivial even for IID statistics, IID random variables. For example, to derive this result is not completely trivial. I'm not showing you how to do that, but but the point is that they are non-trivial, and moreover, they are all universal. I mean, you're not doing, you don't have to do it for exponential, Gaussian, uniform separately. They all have the same answer. Okay, so it's totally universal, and for any n, and this is the beauty of this record statistics for the. So essentially, you can calculate all this, and this is used as a sort of I mentioned in my first lecture, there are many applications. For example, avalanches in disordered systems, or type 2 superconductors, vortices in type 2 superconductors, and creep motion in spin glasses, and so on. So all these places, So they are in the context of, when you pull a polymer through a disordered medium, they get stuck for a while and then they move. So, this is like the avalanches basically. So it sort of stays there for a while and then suddenly the center of mass jumps. And so you have this, so essentially the number of avalanches is sort of exactly the number of records and so on. I mean, they're intricately related to each other. And people have applied this IID, model to understand many of these record statistics in various different avalanche models and so on. And as I said, this is quite beautiful. And there are many other interesting problems. So people study, for instance, I mean, you can ask, okay, here, your criteria for record was that if xk is bigger than the previous guys. So that means all of them, or if you like, a maximum of but sometimes, I mean, people introduce an offset parameter called C records. So you say that a record happens at these things if its value exceeds the previous record value by at least C. So it's not bigger than this, but it's bigger than this value plus C. Only then it's a, if it is less than that, it's not a record. But only if it exceeds this. So C equal to 0 is the case we discussed. And what happens for finite C? And this is an important model in evolutionary biology also. And so there's very interesting statistics for that. C can be positive or negative and many other things. Okay, so these are the different models that people study. And so what I'll do is maybe we can take a break now. And then in the next lecture, I mean, I just do the same thing for random walk model. Okay? Is there a tea? Yeah.
It's quite hilarious. Yeah. They swear they will see, the walk past something in the street. And they just can't do it, right? They just can't do it. And so, every now and again he shouts out stuff and mentions to the side. Maybe the kids will be watching this thing.
Okay, so let's now look at the second model. So I'll do the exactly same thing, record statistics, but for the second model, which is the random walk model that you have been doing all through. So it's a example of correlated time entries. So remember again, xn was xn minus 1 plus eta n. So this is the current location after step n of the random walk, starting at the origin. And now the noise, they are IID variables. Each drawn from some noise distribution, which I'll assume to be symmetric and continuous. So for instance, if I look at the trajectory, it starts at the origin, maybe it does this, typical trajectory. So again, so this, okay. First guy, I mean, I'll take it always as a record. Anyway, it starts at the origin, so it's not really important. So this is a record, this is a record, this is a record. The rest of the guys are not records. Okay? So again, the criteria for a record. If the position of the worker is bigger than all previous guys. So if you think of as an animal performing random walk in space, let's say in one dimension, then whenever its position exceeds that any site that it has visited before, so that's like a new site in its trajectory, so it's a record. Okay? And again, I mean, we'll calculate the statistics of M, which is the number of records. Okay, so as before, like in the IID case, we can write this M as summation of sigma k. K goes from 1 to n, where the sigma k's are these binary variables, either 1 or 0, if the kth entry is a record, and 0 otherwise. So let's first calculate again the mean number of records. So that would be k equal to 1 to n expectation value of sigma k, where this record rate sigma k is just the probability that a record happens at step k. So earlier for IID variable, this was very simple. It was 1 over k. Now what's the answer? Okay. So let's look at it. What is this object again in terms of trajectory? So suppose my trajectory is something like this. So I started at the origin, and I know that a record occurs, and I want to find out the probability that a record occurs at state k. So suppose that such a record occurs with the record value r. So this is the record value r. So this value here is r. So then average sigma k here is the probability that a record occurs here with record value r, and then have to integrate over all possible values of r. So now you see, interesting, now it will connect with previous lectures. So this object, if a record occurs at here with a record value r, so all I have to do, I don't care what happens after that, right? This part is totally irrelevant to me. I'm just asking what's the probability that a record occurs. So we can forget about this part of the trajectory. It can go up, whatever, it doesn't. I'm just interested in this part only, right? What's the probability of the record there? So if this guy is a record, that means at all the previous steps, it must have been less than r, right? So again, if you like what we were doing in the last class, if I shift my origin to this line and look downwards, this trajectory, so you'll see, so this is like new origin if you like, and I'm just going in the reverse direction. So I'm jumping from here, so if you like, shift the origin and reverse the time. So then you will make a big jump here, then and then you come there. And I'm measuring my distance from, so the final value See, from this point of view, if I go look downwards, I'm arriving at distance r, right? This is my new origin, so I'm arriving at a distance r, starting at the origin. This is my origin. I'm arriving at r, but here in this example, staying negative, but if I reflect this path, that's like staying positive, okay? So the sigma k, therefore, now what is the probability that I arrive from 0 to r staying positive? So this is exactly the restricted Green's function that we had computed. So remember, restricted Green's function was this, that if I start from x naught, what is the probability that my random walk arrives at x in step n? So that is what we were defining, so without crossing the origin. And we showed that this was a very hard object to compute, but this is exactly what you need. You need to arrive at r, starting at 0, so the x naught is 0, and in step k. So this is then exactly g plus of r 0k, and I have to integrate over all possible values of r, right? Because this value, it could have been here, it could have been there, anything from 0 to infinity. So this is therefore exact result. So this is the restricted Green's function integral dr, okay? But you remember, I said last time that if I integrate over the final position, from 0 to infinity, this is just a survival probability. That means starting at x naught, what is the probability that the walk does not cross the origin up to step n? So therefore, this is nothing but the survival probability of this guy starting at the 0 till step k. But you remember in my last lecture that we said that if you start exactly at the origin, then that particular special value, that is, what is the probability that the walker starting at the origin stay positive up to all step n? This is the famous Spar-Anderson result. It's totally universal. Universal for all n. We derived this result in last class. So therefore, what we have, sigma k average is just 2k, choose k, 2 to the power minus 2k. Once again, this is universal, does not depend on the noise distribution, whatever be the noise distribution, as long as it's symmetric and continuous, okay? So therefore, the mean number of records is sum over k equal to 1 to n of sigma k. So this is you can do this sum very easily. So this is just a binomial. So that's the exact result. For any finite n, the mean number of records is given by this universal formula, which is independent of. So for Levy flights, for Gaussian walk, for uniform random walk, for every random walk, this is exactly our answer. Okay? And it's universal for all n. It's pretty non-trivial result if you think about it. So this result was derived in a paper with Bob Ziff. Okay? But actually, this is a more general result. This I will show now. Now we want to go to calculate the distribution. But the mean has a very nice simple formula. And in particular, now if you take the large n limit, so in the large n limit, again, you can use Starling's formula to calculate, this is just 2n factorial divided by n factorial. So you can just easily calculate the Starling using Starling theorem, Starling's approximation. And the answer is that this is square root of pi times square root of n. So the mean number of records grow much faster. Remember, IID case it was growing like log n, but now it goes like square root of n, which is not surprising because, for a random walk, which is not surprising if you think of random walk, if you say, naively you would have said, okay, random walk it will go like square root of n, therefore mean number of records is roughly square root of n. This is totally wrong because this is true even for Levy flights. So Levy flights typical displacement grows like, n to the power 1 over mu, where mu is the Levy index. So it's not always square root of n. So this square root of n has nothing to do with the typical displacement of the walk. This is a much more, non-trivial result basically, and it's universal. It's true for Levy flights as well. So it grows much faster than log n, and this is due to very strong correlations between the positions of the walkers. Okay, so this is the mean number of records. And I want to compute now the, let's say, the variance or full distribution. So for instance, if I want to calculate this m square, that will be as before in the IID case, this correlation function. But now it's much harder to compute this correlation function. And in fact, sigma k's are not independent now. They are correlated. You can check that. Up to 2 you can easily, you can do it if you like, or you can just do it by computer simulation. What you find is that sigma k1, sigma k2 is certainly not equal to sigma k1, sigma k2. And again, this is due to the strong correlations between the xi's. Okay. So then how would we proceed? Because IID case, it was very nice because you could show that all these are independent variables, and then you just calculate the distribution just by taking the generating function and using the fact that they are independent. But now I can't do that. Okay? So you need some new method to compute this. And this is the method that we used with Bob Ziff, and is based on something called renewal approach. And I'll explain to you in a minute what this is. So let's draw a typical trajectory of our random walk. Again, we start at the origin. So let's take a configuration like this. So here you cross the origin and you reach a new record value. And then maybe do this, choop. This is the record. And then again it does this, maybe less, and makes a record. And then it does this. So in this example I have, okay, this is always record. So 1, 2, 3, 4 records. And as before, these are the record edges, right? This is L1 is the number of steps that this remained a record, then it got broken. L2 is the edge of the second record, L3 third record, and so on. And the last record, which is yet to be broken, so that is just LM, if there is M number of records. M is the number of records in the configuration. And collectively, as I was doing before, I will denote by this vector L, these different edges of these records, just for notational convenience. So what we want to calculate is P of M, just the distribution of the number of records. I mean, so happens in physics that often, in many problems, you have to identify the right set of variables. So sometimes it pays if you actually make the system, make the question more complicated. Okay? You are looking for the statistics of M, but you say, okay, maybe I'll get to M, but maybe there's some simplification if you look at a bigger object, more complex object. The idea is that, it's like, sometimes if you think of, let's say, I have n random walkers in one line. On a line. Okay. So, this, you can either say that, okay, this is a single walker in the n-dimensional space. Okay, so you make the problem simplified in some sense, but by extending the space. Okay, so in this problem, you will see that I want finally this object, but actually it pays. It's not easy to write down an expression for this directly. What is easy, however, if you look at the joint distribution of the L vector, that means joint distribution of all the edges and the number of records given total number of steps n. So this is a much more complicated object, right? It's like a joint distribution of many variables. But the idea is that if you have such a thing, if you can compute, and then if you integrate this object, then is just a marginal distribution. So you just integrate over all these DL1, DL2, DLN, etc. Okay. So you calculate the joint distribution, which happens to have a nicer structure, and then you just integrate out the edge degrees of freedom because it has much more information. If you're just interested in only one of them, in this M variable, you just have to integrate out the other guys, and that gives you the marginal distribution of Mn. And now we'll see that while I could not write directly an equation for P of Mn, unlike in the IID case, but I would be able to write an expression, exact expression for this joint distribution. Okay? And let's see how we do that. So to do this, we have to do few little steps, and then I have to define two objects for a random walk. Forget this for the moment. Just think of this object. So I have a random walker. You start at x0, and you're asking what is the probability that the first step I stay below x0, my x1, this is x1, x1 is less than x0, x2 is less than x0. So basically I stay up to step L, I stay below the level at x0, initial point, right? So I call this Sx0L. what is the probability my walk stays below the starting point up to step L? Okay, that's exactly this object, which is the same as because again, if I shift, because this walk configuration, you could have started x naught, you could have started origin, you can shift your origin here, then this is just exactly same. It doesn't depend on the starting point, right? So it's just exactly the probability that starting at the origin. So if you call this is my new origin, then it's just a probability that starting at the origin, it stays below the origin, because it stays below the initial point is the same. This configuration doesn't depend on x naught really. So I can just make a translation there, okay. Shift. So this is the probability that the walker starting at the origin stays below the origin up to step L, right? But this is the same as because this walk is symmetric. So this is exactly probability that starting at these things, I stay positive, because staying negative and staying positive is exactly same because it's a symmetric distribution of the noise. So therefore, this is just exactly the same as the probability that starting at the origin, I stay positive up to step L. But this is precisely our Q0L that we had computed before, right? And by Sparr-Anderson theorem, this is given by this. Okay, so that's the first object. What is the probability that up to step L I stay below my initial point? And I'm asking this question because this is exactly what you see that, you sort of stay below this and then you just go over this, okay? So this is the second object. I'll define also. So this object, as you see, it does not depend on the initial position x naught, right? Just because of shift. So I define FL, which is the probability that first step, it stays below the origin, second step stays below the origin, L minus 1 step below the origin, and the Lth step, it becomes positive, starting from the origin. So that means I'm looking for configuration or up to L step, it stayed below it, and then the Lth step exactly, it went over the initial position, or origin basically. Okay. So this is called the first passage probability because you go between step L minus 1 and L, you cross the origin for the first time. And how do I calculate this object? You immediately realize this is just Q0L minus 1 minus Q0L. Because Q0L minus 1 is the probability that you stay negative up to step L minus 1. Out of those paths, some of them will cross the origin, the starting point exactly between L minus 1 and L, and some will continue to stay negative. So if you look at the fraction that's continue to stay negative, that is exactly Q0L. This is the probability that the walk stays negative up to step L. So the difference between that are the paths that have crossed the origin exactly for the first time between step L minus 1 and L. Okay? So just think about it, it's obvious, okay. So therefore, we know the answer also here in terms of the Sparr-Anderson theorem. This is, in particular, if I take a generating function of this, because this is something we'll need. So generating function of that, you remember, of Q0S. So for Q, this we had shown in the class, Q0S, which is Q tilde 0S, which is Q0L, S to the power L, sum over L equal to 0 to infinity, which is just multiplied by S to the power L and sum. And this is trivially 1 over square root of 1 minus s. This is the Sparr-Anderson result. And now if I do the same thing here, f tilde of S is, so you multiply it by S to the power L and do the sum. So this will be just 1 minus and this is universal, so first passage probability is also universal. Okay? So we have this Laplace transform. Generating functions are given by these two expressions. Okay, so why am I defining these two objects, right? So let's now go back here to our picture here. So what you see, I'm looking at, this is the probability of the full trajectory specified, characterized by this L1, L2, L3, Ln, and the number of such intervals, which is m. Now these intervals, you see this guy here, it stays below here, and then it jumped from step L1 minus 1 to L1, it jumped because that's when the record occurs, right? Because this value exceeds this, that means it must have gone beyond its initial value. Okay? So this is record number 1 and L1. So what is the probability of this segment? So this is exactly our f of L1, right? Because you stay below up to L1 minus 1 level and then jump for the first time at step L1. So that's exactly that. What about this guy, second guy? That's exactly FL2. And I'm making this as a product because of the Markov property of the process, because once you specify this here, what happens after that is totally independent of what happened before. Okay? And therefore this is just a product of these things. So similarly FL3, and we'll go up to FLM minus 1, except, so this is the L length Ln minus 1, except for the last guy, which is this Lm, because last guy, it has not crossed yet, right? So this is the last record. So that, therefore, the probability of this part, which is not yet completed record, so that is just the probability that this path stays below this level, and this is exactly Q0 of Lm. Right? So I'm just making the product of different segments like this, and the last segment is slightly different from these guys, previous ones. And then I have another constraint, which is that the sum of all these lengths, this is exactly n, because I have total number of n steps. Okay? So you can think about it, and you convince yourself that this is an exact answer. Okay? And this uses this renewal because after every record, the process itself renews. Okay? That's why it's called the renewal process. And you just have to compute a product of the first Lm minus 1, and the last record is slightly different from the previous m minus 1 guys. So it's Q0 Lm, it's not yet complete, the record. And you have a constraint that the total length must be equal to n. So this is exact answer. Okay? So from this, I want to integrate over L to calculate this. So this is done, most sort of economic way of doing this is to actually first consider the generating function, because you have a delta function here. So the L1s are not uncorrelated because their total sum is fixed. So therefore, you want to get rid of that constraint. So how do you get rid of that constraint? Whenever you have a delta function, you just take a sort of, in this case, since it's a positive variable, so take a generating function. So I'll define so when I multiply it by this guy by s to the power n, so it becomes, so this multiplied by s to the power n, okay? And then if I sum over all L, so when you multiply by s to the power L, it becomes s to the power L1, s to the power L2, s to the power Lm. minus 1 s to the power lm, right? And take this factor with this guy, take that factor with this guy, and lm with this guy. So you convince yourself that this is nothing but exactly this, whatever we needed. This is a generating function of each guy. So there are m minus 1 on such guys, and then this is just q tilde 0s, which is also specified here. So the answer, therefore, is f tilde of s to the power m minus 1 times q tilde of 0s. And we know these things explicitly. So what you have is 1 minus square root of 1 minus s to the power m minus 1 divided by. And since when I integrate over sum over all L, this is just exactly, therefore, generating function of my number of records, sum over n. Generating function with respect to n, not with respect to m. Okay? So this is it. It's totally exact answer. So first thing you notice, the whole jump distribution doesn't appear at all explicitly, which means this is again a total universal result. So the full distribution itself is not just the first moment itself, but all moments, full distribution is totally independent, universal. And you can in fact calculate everything from this expression. So for instance, so if I have this expression, so let me write it down here again. So the main result is that P m comma n s to the power n sum over n from 0 to infinity, this is equal to okay. So if I want to calculate the mean, so I just have to multiply it by m p m n sum over m. So this means but you know how to do this geometric series. If you have x to the power m goes from 0 to infinity, this is 1 over 1 minus x. So if I take a derivative, okay. So if you take the derivative, so what you get, the answer is 1 minus s to the power 3 by 2. And now you just expand this guy in power series, and then find out the coefficient of s to the power n. So that gives me the mean. This is just a mean. Is precisely what we had calculated before using this sigma method. And this for large n, as we showed, goes like 2 by pi root n. Okay. And now you can easily calculate the variance. Second moment, for example, for second moment, you just have to multiply by m squared. So that will be m squared there. And again, you can do this series, take one more derivative. I will not do it in detail, but m squared so anyway, you can easily check. This is so again expand in s and read off the coefficient of s to the power n. And what you find is that m square, this is exact again for any n. Okay, for large n, this goes like 2 times n. So the second moment goes like 2 times n. So therefore the variance of m. So again, remember that we could not have computed this using this sigma method. It was much more complicated. But we bypassed this whole thing by doing a bigger object, which I could write down an explicit formula using this renewal property. And then I just integrated out the L to get the distribution of m. Okay? So it just illustrates that what I was saying, namely that sometimes it's easier to complicate the problem a bit more, and then some simplification occurs. So you see a pattern basically. So therefore m square minus average m square, and if you calculate this, and then again you can compute this, what happens in the large n limit. So this goes to 2 into 1 minus 2 over pi times n. So therefore the width or variance fluctuation of the number of records also grows linearly with n, but with a very non-trivial universal prefactor, 2 times 1 minus 2 over pi. Okay? So again, all these statistics is totally universal. And indeed, okay, I'll not do it, but you can, this is just moments, but you can actually even calculate the full distribution explicitly just by looking at the coefficient of s to the power n. This is a good exercise. I leave it as an exercise. How to calculate the coefficient. So you take this expression here. How do you calculate the coefficient of s to the power n on the right-hand side? Okay. You can do it, and the answer is, so basically you can use what is called the Cauchy's theorem. So this will be ds in the complex S plane, 1 over 2 pi, 1 over s to the power n plus 1 times this object. So this is a complex integral. You can, by making a change of variables, you can do this complex integral explicitly. And what you find is this beautiful answer. Which looks very simple, but actually is like exactly like Sparr Anderson. It's quite non-trivial formula. So this is exact for any n and m. And not only exact, this is again totally universal, that is independent of the noise distribution, as long as this is symmetric. So you see, this Sparr-Anderson theorem is very powerful. We have used this Sparr-Anderson theorem in many different contexts, maximum records and so on. And here, this is another example where it gives you the exact answer for any m and n. And in particular, so you can again do our usual favorite game. That is, okay, so this is the result with ZIF. Same paper, basically, 2008. And in the large m and n limit, so if I take the large n limit, again I can use Starling formula to evaluate the asymptotics of this. What you find is that P of mn converges to some scaling function like this. And this scaling function g of y, again, is just exactly the half Gaussian that we came across before when we were calculating the distribution of the maximum of a Brownian motion. Okay. So, but here it has now, here this is a, a square root of n scaling. It's very, very different from the maximum, because maximum depends for Levy flights as n to the power 1 over mu, but here it's a totally universal. This is result holds even for Levy flights. So that means if I plot this scaling function g of y, so it looks like this half Gaussian. Okay. And this is a completely fully universal result. Okay. And then there have been many other problems in which this technique of renewal process has been applied. Sanjeev, for example, has generalized these results to the case of records for continuous time random walks. It's called CTRW, continuous time random walks. So this means basically that after every step, so here you are jumping instantaneously, but you introduce a real time, not the steps, and you say, okay, so it makes a jump, and then it waits there for a certain amount of time, which is drawn from some distribution, typically a power law distribution, and then again maybe it jumps instantly, and then it sort of waits for somewhere random time, and again jumps and waits for a random time. Okay, so these are called continuous time random walks. So the waiting time is drawn from some distribution. And this is the real time t. So the number of jumps is also a random variable in this case. And for these, he could compute, for example, the number of records up to step n, and again, showed that this is independent of this jump, waiting time distribution and jump distribution, etc., etc. And I mean, it's not always, but at least for a class of this. And this is so this universality always employs this underlying Spar-Anderson result essentially. And then, more recently, we have also used this for active particles. So if you look at these records for active, when this motion is not a random jump, but there's an active particle motion, that means it's a run and tumble motion, as I mentioned. It goes ballistically up to a random time in positive direction, then switches direction, goes to the negative side. So again, for that process, you can again ask what is the distribution of the number of records. And again, it's universal, but in finite time t. So here it will be P of mt, basically. And there also, for the active particles, you can calculate this P of mt. And this is again completely universal, that is independent of the if you like, in fact, independent of dimension and the jump process and everything. So this is again some recent work with my graduate student, Mori, Vishal. 2019, 20. So, okay, so that's the sort of, and then, but you have a more general information because I rubbed it, P of Mn, but we have the full joint distribution of the record ages and the number of records. So you can calculate the age statistics also. I'll not do these things in the class, but just to mention some result, as I mentioned for the IID case. So here also, if you calculate, for example, the longest lasting record, what's the average value of L max? So what you find, like in the IID case, it grows linearly with the number of steps, because the largest one is, but this constant here is different. So this constant here we computed, so this is given by this formula. And everything you can derive from this joint distribution. So that's the point I'm trying to make. This numerical value is again 0.6265. It's very close to the IID value, but not exactly same. Okay. And the L min, the minimum, I mean the shortest record, the age of the shortest record, so that scales, this is for large n. That scales for large n as 1 over square root of pi times square root of n. So there you remember that in the IID case, the L min was scaling like log n, and Lmax was scaling like n. And now here for the random walk, this scales like square root of n, and this scales like n. So in general, for the correlations between the entries, if you like, they make, there's many more records because you have a jump, you have a higher possibility of jumping and breaking the previous records for random walk, and this is due to the strong correlations between the entries. So, and then you can do many other things, but since we are running out of time, so I just use the last 10 minutes to just to give you a summary and conclusion of these lectures.
So although there are more records,
Yeah.
but the shortest record time is also increased.
Short.
From 10 to root n.
Yeah, log n to root n, yeah, the length of the shortest record, I mean, the survival of the, so you ask, how long will the shortest record survive? So that will be bigger than the IID case. It will be square root of n as opposed to log n. Oh, I didn't mention the CTRW, this was Sanjeev. $2009, 10, 12. I think it's 11, no? Okay, so I mean, basically what you see is that, in all these problems, first of all, it's sort of mathematically interesting, but apart from mathematical interest, it's also there's a lot of application, as I mentioned in my first lectures, okay? So that's what makes this subject very interesting. I mean, you can calculate many things analytically, and still, it has many, many different applications, okay? So that's what makes this subject very, very interesting. Okay, just summarize. So, I mean, basically what in these 10 lectures, so I discussed statistics of extremes and records. In random sequences. And mostly this scope, it was based on the book that I mentioned. And so here that we recently published with Gregory. And here essentially the picture I was trying to always alluding to is this time series picture. So you have a time series with n entries. And in the most general setting that, okay, so there are two steps. Okay, most general setting. So these guys are distributed by some joint distribution, which you may or may not know. And then given this joint distribution, we are interested in various observables, right? So for example, one observable was this maximum, extreme value statistics, or minimum, or the time of maximum, number of records, etc. Those are the observables, okay? So there are two steps to this general class of problems. So as I said, and the time series, it could be, we mentioned, temperature time series, or rainfall, stock prices, or random walk, etc., etc. So many, many, many different, or eigenvalues of a random matrix, etc. So generally that's the sort of general setting. And as I said, when you get a data of a time series from whatever these things, so there are two steps to this general problem. So step one is to figuring out what the joint distribution is. So this is the modeling part. Because often we don't even know how they are distributed, right? So this is the, basically in some sense, if you like, the domain of statisticians, because they actually work with real data, and from this data they try to infer what would be an underlying model so that you can write down what is the sort of joint distribution between the different observables, okay? And the step 2, which is equally non-trivial, so this is already a non-trivial thing. If you like, this is the kind of phenomenological development of a model. And the step 2 is actually given this joint distribution, you compute observables. And this is also a non-trivial thing that I tried to show in these lectures. Observables like EVS, for example, X max, or the time of the maximum, or the, you know, what I didn't do in the class is order statistics, second maximum, third maximum, etc. And then, you know, records, all these extreme observables, statistics of such things, you want to compute given the joint distribution. And this is the second step, is where the statistical physics comes in. I showed you in the class, you know, how you can interpret this as a problem of n interacting particles, and in the presence of a wall. Okay, so that's the sort of statistical physics system, and you can use many of these techniques from statistical physics to calculate some of these things. And so statistical physics is useful. So these are the two steps. So this is the statistics, and this is physics. And in particular in these lectures, what I stressed on the role of correlations. Correlations between the entries. Okay. And so we discussed 3 situations, totally uncorrelated, which means that the joint distribution factorizes and even in this simple model, you know, computing the extreme valued statistics, or for example, time of the record statistics, etc., they are highly non-trivial, and but you can do it exactly, and all these statistics you can compute precisely. And we figured out that what are the different universality classes, like you know, Gumbel for the EVS, Frechet, Weibel. These are the three fixed points for the centered and scaled distribution of the X max. And for the record statistics, you have seen that there are also universal distributions for the average number of records, or the full record distribution is given by the Stirling number, unsigned Stirling numbers. And the second situation, but then you say that, okay, this is a good model, so statisticians use this as a null model, because you know, you have to always compare your actual situation with something that you know, like the experimentalists use something as a control system. So here, you know, you can use and compare to this particular thing. This is called the null model in statistics. So it's very good to benchmark, basically. Okay? So anything that you observe and you compare with the predictions of this IID model, and if it matches very well, then you would know that the entries are more or less, you know, uncorrelated. But if it doesn't match, then you know that there is a problem. I mean, it's not correlated. And also this, because of the universality, these are sort of distribution-free test, basically. So there's like Kolmogorov test and so on in these things. Okay? So this is very useful. And the second situation is when we talked about when the variables are weakly correlated. And this simply means that if I look at the xi, xj, they are connected part, that decays typically with a correlation length, and this correlation length is much, much smaller than the system size. That's what I mean by the weakly correlated case. And there we argued using this kind of block renormalization group argument that, that under renormalization, under blocking, the EVS, the extreme value statistics for large n, the asymptotic EVS, it converges to the uncorrelated fixed points case. So not only that this is uncorrelated model is useful as a null model, but there are actually real systems where there are weak correlations between the variables, and then in the large n limit, you know, they essentially, if you look at the distribution of the extreme, it goes into the uncorrelated fixed point. So they are actually you observe them in real systems with weak correlations. And then finally, the third thing was the strongly correlated case. Where this correlation length, if you like, is much, much bigger than the system size. So they are very strongly correlated. And there, in general, we don't have any general theory for that. So what we have is few models where you can actually compute exactly. So one example of is the random walk in one dimension that we did in great details. And this is a model which is highly non-trivial because many people, many physicists, even if you ask them random walk, they'll say, this is vanilla Brownian motion, what is there? I mean, this is a completely stupid statement. Random walk is a very, very important and very non-trivial subject, and it includes not just Brownian motion, but Levy flights and other things. So that one is to be, but it is still many things you can actually derive exactly, and it's one of the rare strongly correlated system for which you can actually say something explicitly. So right now this stage we don't have any general theory for strongly correlated variables. What we have is few models where you can calculate things explicitly and exactly, and so it's at this stage where you are wondering if there are, like here you have only 3 fixed points. Are there only a finite number of fixed points, or what is it? I mean, we don't know. So right now, there is no general theory for this. So there's a lot of open problems in this area of strongly correlated systems. I give you some examples in my of such strongly correlated system. So many examples I gave in my first overview lecture, but I just mentioned a few of them. I could not discuss. They are discussed in my book. So for instance, I discussed briefly the disordered system problem. So this corresponds to, for instance, a polymer in a directed polymer in a random medium. And here you are interested in the ground state energy. And it's now known that this is given by something called Tracy-Widom distribution, okay? The distribution of the extreme max. So this is a distribution that appears in random matrix theory. In fact, in 2006, David and I, we didn't know anything about random matrix theory, and we were in Cambridge together, and we just walked into some seminar and we saw somebody talking about random matrix theory, and we started thinking about it. And in fact, I mean, this is exactly a problem of strongly correlated system. So this is related to random matrix theory. And as I explained, so basically you have an n by n Gaussian random matrix. You diagonalize them, Hermitian random matrix. So let's say these are the eigenvalues. And then you want to know the largest eigenvalue. And again, these guys are strongly correlated because you can calculate the joint distribution of the eigenvalues. I did not show that explicitly in the class, but it's something like this. So let's say this is a real symmetric matrix. So then you just have a modulus here with some normalization constant. So again, if you did not have this term, they will be uncorrelated, it will be factorized. But because of this term, the eigenvalues actually repel each other. The probability that two eigenvalues will be very close to each other will be 0. So this is known as the joint distribution by Wigner, but maybe it was derived even before. And so given this joint distribution, you want to calculate what's the distribution of the largest eigenvalue. Okay? And so it turns out that you can calculate that at this large n limit, and this is what is known as the Tracy-Widom distribution. And with David we had, so this is we had computed actually the large deviation tails, and there's some very interesting phases and phase transitions there. So there's a lot of interesting physics here. And so this is the disordered systems, random matrix. Then, okay, so then you have these interacting particle systems. For example, I gave you some picture of the granular gas under shaking, under vibration. And then you have a condensation of particles in one particular box, and that's an example of a extreme statistics, because the number of particles inside the condensation, inside the condensate, is exactly the maximum of the occupation numbers. So the EVS, and that also corresponds to another example of a strongly correlated system, and there have been many work in that direction. I mentioned some of them. Then the data storage in computer science problems. How do you actually store your data? If you look at these things, for example, if you have many files, when you store it, you don't put them in one directory, right? You make directory, subdirectory, sub-subdirectory. So there is usually a tree structure in which you put your data, and then when you search for a data, you have to search on this tree, and this is generally called the binary search tree problem. And when the people try to estimate search algorithms and find out their efficiency, they are interested in finding that what's the worst case scenario. That means maximum time you may need to find a search element, to locate a data. And so there, again, to calculate this, you need the extreme statistics of the depth of these heights of these different data points. So it's a really beautiful application of this. And here, again, you can cast this problem into this kind of joint distribution, except that these variables, which are the path lengths, they have a kind of hierarchical or logarithmically distributed correlations. But again, you can calculate many things exactly. And once again, this was, initiated with David, and so we did a lot of work with when we were in Toulouse, long time back. So this is again, kind of system for which you can actually derive quite a few nice exact results. Then there is fluctuating interfaces. So in many systems, like you have a fluid interface, for example, between liquid and air, it fluctuates, and then you want to know the maximum fluctuation in space. where does it occur, or what's the typical value of this. So you can, again, this is an example of a strongly correlated system. You can calculate many properties. So this was, we did some work, joint work with Alan Comte. And then finally, there's a lot of work in stochastically resetting. This is the my current research interest. So in stochastic resetting, again, you have a strongly correlated system. There are many people are involved here, Martin Evans, Sanjeev, and Gregory, and other people. So in stochastic resetting means basically, when you search for something by Brownian search, once in a while, with some probability, it is advantageous to go back to your initial position and then restart the search. Okay, and so this mechanism, if you have many particles, you can actually generate a non-equilibrium stationary state under repeated stochastic resetting when you simultaneously reset them. And so this is a system which has a strong correlations in the stationary state, but still the correlations are such that you can actually solve, even though they are strongly correlated, you can solve many of these extreme value questions. So this is some, there are many people here. I'll just mention Biroli, Marco Biroli, who is my current PhD student, Sanjeev, Gregory Scherer, and very recently we did some work with, also jointly with Sanjeev and Manoj Kulkarni. And so on. So, I mean, just to give you a sort of vista of different areas where these questions, extreme value questions come up, and we can actually make some progress. So right now, the research interest is that, try to find as many solvable models as you can to gain some general understanding of this strongly correlated system. Okay, so that's so I hope I have sort of given you a general idea of the area of the research and what are these sort of interesting questions and why are you doing these interesting questions, and this is, I mean, okay, I could not do, of course, many things in detail. It's only 10 lectures, but this book, actually, we discuss essentially this aspect with more details. If you are interested, you can have a look. But otherwise, this is the sort of general picture that we discussed in this class. So thank you very much.